Hello guys, my name is Divyaprakash and I'm a data scientist with over 1.5 years of experience. In this particular channel, I've took up a challenge where I've promised to document each and everything I do as a data scientist in my day-to-day life. So as part of this, we were working on a project where we were attempting to analyze the performance of a ship based upon an maritime dataset which contains information about various features of engine features of a ship along with the fuel consumption per hour. So these data were recorded for each hour, and the specific features were noted for each of those hours. And our goal was to forecast the fuel consumption using these set of features. So as part of that, we did some exploratory data analysis, did some data cleaning, and prepared our dataset for an LSTM based time series forecasting model, and that was the progress so far. In this particular video, I've built the entire LSTM model and did forecasting with it, and then I've also tried another technique to do the forecasting better. And yeah, so this video will be more focused on that particular area. Let's just get started with that. Before we actually get started with the code part regarding the forecasting model, let us first try to understand the difference between a single step forecasting and multi-step forecasting and how the error propagates in both the cases. A single step forecasting is nothing but when we have a time series data. Say for example, let us take this particular row or this particular column as our input data. So each value will represent each time steps. So if we try to predict the next particular time step value based upon the previous value, so that's how a single step forecasting model works. So where each output is dependent on the ground truth value of the previous time step. So here if it is the 0th hour, so this 0.49 is the prediction for the first hour, and 0.45 is the actual first hour value. So using that, we'll be predicting the next hour. See, we are not using the previous prediction to do the next prediction. We are using the ground truth to do it. So basically, in a business context, it would say, like, if you're attempting to predict the fuel consumption for the next hour, we can do it. But this won't counter the place where we need to predict a sequence of hour from the current state. Say for example, if you are trying to predict the next 12 hours of forecast based upon the current value or the current trend, a single step forecasting can't do that. It at the most it can just predict for the next particular time step. That depends upon the frequency of data we have. In our particular case, we have the frequency of 1 hour, so for the next hour we can predict using single step forecasting. But when it comes to multi-step forecasting, so where like we try to predict based upon the previous forecast. Say for example, this particular row, so this is the ground truth, so this will be going as an input to the model, and 0.49 is the output. And in case of the second one, the ground truth is 0.45, but we don't know that at that particular time if we are predicting for a next sequence of hours. Say for example, at 0th hour, for the 0th hour we'll be doing the ground truth, but for the first hour, which is in the future, we don't actually have that ground truth for that particular value, so particular time. So what we'll be doing is we'll be taking the forecast value. 0.49 is the forecast value for that particular time frame at 0th hour, so we'll be using that to do the predictions. So similarly, this will happen until we reach the final prediction horizon. So in such a cases, so this is actually the residual. So in single step forecasting, since we are actually using the ground truth to do the prediction, so the prediction is just based upon the previous value, that is the ground truth. But in case of the multi-step forecasting, so each step is dependent on the previous step values, so any errors in any of those intermediate step will actually propagate. So that's the reason why when you are plotting the residual plot, it is like, it is in a similar fashions, there is no much variations. But in case of the multi-step forecasting, you can see a very large variations or standard deviation, because each step is dependent on its previous steps. So as we progress to predict more, so more numbers of steps or intermediate between those particular time frames. So it is dependent on more previous forecasts. So the error tends to propagate in case of a multi-step forecasting. So that's a kind of basic understanding and basic understanding we need to have on the difference between the single step forecasting and multi-step forecasting. I'll give more details on that when we actually work on such things in this particular video. So a simple change right now, I've shifted all my progress from Google Colab to Kaggle, because for some reasons I'm not able to use the GPU resources in Colab. Like right now I'm not using any GPU as of now, but in the future I might need. So I've shifted everything to a Kaggle workspace. Oh, so everything is same. So what all the progress I did is the same. Just I have shifted from Google Colab to Kaggle. So yeah, so the progress that we had in the previous video was till this part where we actually created our train loader and test loader, like prepared our data set for our LSTM model. So the sequence length that we took was 6 hours. So we had a previous 6 hours of context for the model to do the actual predictions. So yeah, that was the kind of setup we had. And yeah, coming to here, so this is kind of a information that we need when we work with LSTM models. This is regarding the shapes of certain things, like for example the output shape, the hidden state shape, and the input shape, in required shape by the model, like the way the model accepts our input. So these are some of the informations that we need before we actually build the model. And this is the model definition. So first we need input size. Input size basically represents the number of features we have taken. So in this particular case we have taken the previous fuel consumption, previous high spike flags, and previous low spike flags. So these details I have discussed in the previous video. So that's basically the input size. And hidden size, we can take anything as per our wish, but I'm going with a convention of 64. And again, number of layers is, again, anyone can take any values, but I'm going with 2. And the output size is 1 because we need a final single fuel consumption value for the next particular time step. So that size is 1. And the layers, coming to the layers, so it is going to be one LSTM layer, and then that's going to be another. So the output of the LSTM layer will be going into a linear layer, and then from the linear layer we'll be projecting it to a single value. So that will be our future fuel consumption value. So from the LSTM output, we'll be focusing on the hidden state, because the last hidden state will have the contextual information of the previous context. Here we are giving last 6 ground truth values. So those context of those last 6 will be stored in the final hidden state. So the final hidden state will be of shape 64 because that was the size we are giving. So we'll be projecting that 64 sized tensor into a single value tensor. So that single value tensor will be our fuel consumption of the next time step. So that is a very simple LSTM model, nothing fancy here. So that's what I'm doing. Like I'm getting the output from the LSTM layer, taking the last hidden state, and then fitting it into a linear layer, and then I'm getting the final output. I'm just returning that. So, and for the criterion for the loss function, I'm taking MSE loss. So that's again a convention for regression problems. So, and for the optimizer, I'm going with stochastic gradient descent, and learning rate I have set it to 0.01. So these are value I came up with trial and error to make my output look better, for better accuracies. So those were the choices made upon that. So I tried different things and I came up with this finally. And I'm just changing the devices to run in GPU. And yeah, this is my training loop. I'm just getting the X and Y in batches, and then I'm getting the outputs, computing the loss, doing back propagation, and logging the loss for each epoch. So this will run for the number of epochs we choose. I've chosen 15 epochs, and I'm just training the model. And this was the loss trend I got. It was gradually decreasing. it was good, it was fine and good. And then I did my predictions then, and I got a test loss of 0.064. So the same process, just I'm not propagating the loss back, I'm just recording the predictions and then storing them. And once I got the predictions, if you remember, before fitting it into the model, we kind of did a normalization. So if I'm not discussed that before, so what I did was since the fuel was in the range, if you look at the plot, it was ranging between 500 to 2500. So any model that we use, it is not a good practice to fit the model with the direct values, so we kind of need to standardize it. So the formula to do this is x minus mean divided by standard deviation. So I did that. I believe I mentioned that. If I'm not mentioned it, so this was the function that I used for that. So I'm computing the mean, standard deviation, I'm just normalizing it using the formula that I did. So it will bring down the value to a much smaller scale, which will be helpful for the model to do better predictions. So if we are doing such transformation, our predictions will be also in that particular case, but our final prediction should be again same in this particular scale. So we need to somehow transform it back. So we need to have the mean and standard deviation value for this original distribution and do the reverse transformation. So that's what I am doing. That after getting the predictions, I am just doing the reverse transformations using the standard deviation and the mean. So I'll now be getting the predictions in the original scale, and what I'm doing is I'm creating a data frame with the date range, predictions, and the actual ground truth values, and I've plotted it. So I had a red color for the actual case and a green color for a prediction, how to see how both are aligned with each other. So I plotted it. So this was a plot I got for it. I'm not very sure if it is clearly visible to you guys, but yeah. So the red ones, as I mentioned earlier, represents the actual value, and the green ones represents the predicted values. Somewhat it might look good, but there are some key issues here. Like for example, the dips are getting overestimated. It should stop at around somewhere around 600, but it is going way below it. And when it comes to the high peaks as well, even though it is able to understand where the peak is it actually is, but the peaks are getting underestimated. Instead of predicting a value around 1300, it is predicting around 1000. So we have a difference of 300 units. That's very huge in this particular context. Also, there is a slight delay in which the actual predictions are getting done. Say for example, if we are getting a peak at t0, but the model is predicting at t2, so but the issue is we need to get those things at t0 itself. That's a concern here. So if you are getting a peak value, we need to make sure that our captains know such things is going to happen. So those things are very crucial here. Even though it is a very minute thing, it is just going to be predicting at t2 or t3, but we need to have them at the right point. So that's the key issue here. So we had those issues in case of LSTM model. So one is the underestimating and overestimation of the tips, and as well as in the x-axis we had slight delays in the way the model was predicting it. So those were the issues with the LSTM model. Of course, this can be this can do better if we had some other features within our model which can represent those anomalies, specifically since the output depends on various other input features like the torque, the wind speed, the way in which the geographical locations. So those are some other external features that would affect the fuel consumption. We didn't take that into account. We just took the time value and the spikes as a flag to indicate the spikes, a high spike or low spike. So yeah, but that was the issue with the LSTM model. So what I did was I engineered some features and tried to build an tree based model like XGBoost. So what was the reason behind it is like LSTM models are good to do time series forecasting, but they need a large number of data. The data I had was around 700 rows for training and 200 for test. So effectively, I had just 700 rows of data. In the context of LSTM to do time series forecasting, in some cases that might be enough, but what I thought was LSTM might not be the most optimal solution for this problem, even though it is able to do some kind of analyze the trends well. But if I go for any kind of tree based model which can do a better job for a smaller subset of data, so that was my idea. So I chose XGBoost. So I chose XGBoost to do the predictions. So in case of XGBoost, since like it is a tree based model, it intrinsically not does not have the auto regressive nature of LSTM. So we need to engineer certain features so that the model can be um, made compatible to a task like time series forecasting. So what I did was, so this was the feature engineering function. So first, what I did as same as the LSTM, I created lagged features to give it a context to the previous six values. So if I'm focusing on the T0 and I'm trying to predict the T1 value, I need T minus 1, T minus 2, T minus 3, T minus 4, T minus 5, and T minus 6. So these last six values were first created as a features. And then since we had an issue of overestimation and underestimation of the spike values, so instead of just having a binary column to indicate the spikes, what I did was I engineered a new column which would actually say the difference between the previous value and the present value. This will actually tell the model how far the trend has increased, other than like just saying whether it has a peak or low. So instead of saying whether it is a peak or a low, it also will say how much was the peak and how much was the dip. So that was the idea behind engineering that particular column. So that's basically this one, rate of change. And then I engineered certain time related features because the model should know about the cyclic patterns within the time frame I had, because since it is going to be a data set which is going to range over months and weeks, so there will be some kind of cyclic pattern in terms of days, in terms of hours, in terms of in terms of months as well. So that was the idea. So what I did was, first I got the year, month, day of the week and hour from it. And there was one issue with this, like there whenever we have cyclic data like this, say for example if we are just using the normal coding, because in case of df of month, this will return values from 0, 1, 2, 3 up till 12, and after 12 again it will be 1. So since this particular timeline, it ranges from 2023-10 to this is just the training data. When I go to the just the test data. When I go to the training data, it ranges from 2023 sorry of course, like it is not going from one year to other year, but still, like there is kind of a cyclic pattern within it where it changes from a month to month. Say for example, if we take the day column, if we are computing the day directly, there is, for example, it ranges from 1 to 31 or 30. So after a particular point, it again comes to 1. So it kind of cycles around it. So the 31 and 1 are not separated. There is not a huge gap between those things. 31 and 1 are near to each other because it is the next day. Same happens for month as well. So 12 and 1 are not separated a large distance. I think so. I'm not clarifying it well in my previous few minutes. But what I'm trying to say is, like, these are cyclic quantities, and we need to somehow make sure that the 12 and 1 are close to each other. Similarly, the 31 and 1 are close to each other. Of course, I'm not taking the actual day from here, I'm just taking the day of the week, which will say, like, for Monday it will be encoded as 0, and for Tuesday it is 2, Wednesday it is 3, and so on and so forth. Again, here as well, for Sunday it will be 7, and for Monday it will be 1 again. So those things should be considered as a consecutive values, not so if it is given as 0 and 7, the model will consider that the 7th value and the 0th value are far apart, but that should not be the case. So that's why we kind of transform them using sine and cos functions. So those functions are periodic functions, so we define the period here. So for month it is a cyclic period with a period of 12, and for hour of the day it is 24, because the 24th hour and 0th hour are close to each other. So that was the idea. And for day, again, since it is a cyclic quantity around 7 days, we are providing that as a context to the model. So if we use the sine and cos values of these values, then our model will try to understand things better. So these were some of the features that I created for the XGBoost model. And then again I splitted it using a test size of 0.2. Again, I'm not using a random train test split. I'm splitting it based upon a particular value, and then anything before that will be considered as a past values, and anything that comes after that will be considered as a future value. And then I fitted those things and predicted using an XGBoost model. So similarly how we did for the LSTM model. So just the features are changing, other than that everything is same. The target value is going to be the future values, and the features will be the past values, as well as some transformations based upon the date time column. And what I did was, so again, when I get the predictions, I created a data frame and I plotted those predictions. When we compare it with the LSTM predictions, like I'll just have that here. So this was the predictions from LSTM. So if you can see that, like let me just, yeah. So the peak points are underestimated there. The low spikes are very much underestimated in case of an LSTM model. But in case of the XGBoost, the predictions went pretty good in case of the spike points and the low points. It was able to understand it, the peak better than an LSTM model was able to do it. So that was the one advantage I got here when I compared with an LSTM model. But again, it had some other issues. It struggled to understand the trends, but LSTM did a good job in understanding the trends better than an XGBoost model. But here, again, I didn't have the x-axis issue as well. So the predictions were pretty accurate as compared to the LSTM model. Here we were able to find some kind of deviations in case of the prediction at the right time, but that issue was not there as far as when I visualized that directly when I plotted the actual values and the predicted values. So yeah, so that was some kind of so XGBoost had its own pros and cons, but both models were serving different purposes in case of this particular time series forecasting. But since it was predicting the points at the right time, so this can be a better model to do the multi-step time series forecasting. As I mentioned earlier, so since the in multi-step time series forecasting, each forecast will be dependent on its previous forecasting, and the error will try to propagate. If we have a deviation in terms of x-axis, specifically on the time, then the error will be exponentially high if you use the LSTM model. But since XGBoost didn't have that problem, and it had only problem on identifying the trends, so what I did was it was the same setup, so nothing is gonna change as part of the model development. It's the same model. The only difference is how I inference the actual model to get the predictions. So instead of directly using the ground truth values, what I did, so first I computed the prediction for the first particular sequence. So this is the sequence, this is the first time step that I'm predicting, and based upon that result I'm appending that to the original ground truth value as the last, the very recent past value. So likewise I'm doing this, I'm getting the subsequent prediction, and that prediction will again get appended to the X text. So the X text will be modified in such a way that we are not using any ground truths, and all the predictions are based on our previous forecast. So in this way, like we are able to do multi-step forecasting with XGBoost. So like consider this like so we have a series of context. So based upon that context, we are predicting for the future, depending upon the amount of time that we would like to get. In this case, I'm taking till the end of the X test. Instead of going with the actual values, I'm trying to predict that using the training sets context. So that's what I'm doing here. So again I'm converting that into the original scale, since the predictions will be in the transformed scale. I'm converting that here, and then I'm creating the data frame with the date range, the predicted value, and the actual test set, and actual values in the test set, and then like I'm plotting it, and like it's pretty similar to how the XGBoost worked for a single step forecasting. So it's better that like we are able to transfer that into a multi-step forecasting with a similar results. So but still, again, as I mentioned earlier, the XGBoost struggles to understand the trends. But of course, like I've not used any hyperparameter tuning or regularizing the model using any techniques. So yeah, if I do that, I might get some kind of accuracy, better accuracy. Also, like I can also do some kind of transformation to handle these spikes better, so that the model will be able to understand them. So if I do those things, the model might get better in terms of predictions. But in an higher level picture, XGBoost is good in terms of understanding the spikes, and like that was the major thing that XGBoost was able to do. And in case of, and it is also able to do in an multi-step fashion, because there was no kind of deviation in terms of time steps. For accurate times, it was able to identify the spikes. But in case of LSTM, we had some kind of minor issues in which the model identifying the right time for the right prediction, even though it was able to understand the trends. So one way of moving forward is might like we can go for an hybrid model, where like we can have two models, one to understand the trends and one to identify the spikes. But it's just an intuition, but I don't know how this can unfold. Also, we can go for sequence to sequence LSTM and check how that performs for a multi-step forecasting. But again, since the dataset size is smaller, we need to think in that aspect as well. So I'm not very sure, but in a first steps perspective, we were able to build two models, one to understand the trends well, and other to understand, and other to identify the spikes better. That's pretty much good for now, and it's a good progress from my end. And I kind of computed all the metrics related to the regression: mean absolute error, mean square error, and RMSE. And I created a benchmark for the LSTM, XGBoost, and XGBoost for multi-step, and these were the values I got. Overall, XGBoost for single step was the best model, but XGBoost for multi-step as well is not a very bad model. Like just a small deviation in terms of errors as compared to the single step one. So it is a valid approach, the XGBoost for multi-step as well. So as I mentioned earlier, so this will be our first step, and these are our baseline models in the progress of us trying to analyze the performance of the ship over time and predicting the and doing the fuel forecasting. Yeah, so that's it for today, and like in the upcoming videos we would try to make this model to output results with better accuracies by doing some kind of feature engineering or doing some kind of changes in the model architectures. So yeah, that would be the future of this particular project. But yeah, that's pretty much for today. I just wanted to share how things went with LSTM and XGBoost. See you guys in another video soon. Thank you. Bye bye.